We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello dear students, today we will start the new article, that is Hall effect. This is very interesting phenomenon which correlates the importance or the effectiveness of the magnetic field in order to generate the corresponding electric field. The Hall effect principle has been named after an American physicist, Edwin H. Hall, in 1879, which was primarily considered for conductivity measurements in semiconductors, which was earlier cannot reveal whether one or both types of carriers are present nor distinguish between them. So if majorly we known that if we have semiconductors, then there could be the presence of either electrons, either holes, or there is a possibility of existence of both types of carriers inside the semiconductor. But the drawback of conductivity measurements was that it was unable to detect the presence of single or dual types of carriers or the distinguish between the holes and electrons. However, this information or the drawback of conductivity measurements can be flowed out by obtained from Hall effect measurements, which are a basic tool for the determination of mobility. So Hall effect, we can say that it is an indirect evidence for identification of single or dual charge carriers inside the semiconductor. So on which principle the Hall effect is working? When a current carrying conductor, or we can say semiconductor, is placed perpendicular to the magnetic field. This is very important. The direction of semiconductor, or we can say the angle between the semiconductor and magnetic field, will be 90 degree. After satisfying this condition, a voltage will be generated that could be measured at right angles to the current path. So this is basically a 3-dimensional situation in which the one dimension stands for your investigating material, that is semiconductor or mostly conductor. The other direction will be secured for the magnetic field, and the third dimension will be hold for the current path. And remember, all these 3 dimensions will be perpendicular to each other. As shown in this figure, we have to consider a simple crystal mounted with a magnetic field capital H, that is a symbolic representation of magnetic field in the Z direction. Now we will consider this 3 dimension X, Y and Z. So in the Z direction we have magnetic field perpendicular to the contacts. As you can see, the crystals have 4 contacts, 1, 2, 3 and 4, as already depicted in the figure. 1 and 2 are in the horizontal direction, 3 and 4 are in the vertical direction. Now if current is flowing through the crystal in the X direction, so again after Z direction the X direction is also cleared, which stands for the current flow. In the X direction, by application of a voltage Vx between contacts 1 and 2. So 1 and 2 contacts will have the current flow. A voltage will appear across contacts 3 and 4 in the Y direction. So 3 and 4 will be the output voltage direction. From this figure, the two more parameters which we have to consider are small b and small t. Small t is the thickness of the crystal and small b is the breadth of the investigating crystal. It is easy to calculate hole voltage if it is assumed that all carriers have the same drift velocity. Here the word drift velocity is arised. So basically, when the material or molecule, or you can say at micro level electron, when it is in steady state, and instantly if you are applying the electric field, it will migrate its direction, and this phenomenon is known as drift, and with its corresponding velocity according to which the electron has migrated or diverted its direction is known as drift velocity. So we will identify the calculation of hole voltage in two steps. Step A, by assuming that the carriers of only one type of present, so either electron or either hole will be presented in the material. We will assume that because inside the investigating material we don't know how many charge carriers are present. We have to identify it. So we will take two possibilities. Step B, by assuming that carriers of both types are present. So first of all, we will initiate with step A. Step A, one type of carrier. The magnetic force on the carrier is Fm. The M subscript is used for the force due to magnetic field, and that is known as magnetic force, is equal to, this is a well known equation, EM vector. EM vector is the magnetic electric field vector. Small e is the charge of electron. EM vector is further classified as V cross H. V is the drift velocity of electron and H is the value of the magnetic field, that is in Gauss. So finally magnetic force is given by EV cross H, and it is compensated by the force Fh due to the hole field EH, and hence Fh is equal to EEH vector, that is equal to Fm vector. As V is the voltage along the x-axis and H along the z-axis, the electric field EM is along the y-axis and is given by EM is equal to small v into H. Now see, all the directional quantities have been converted into the scalar quantities by taking the single dimension, and V is equal to mu into E. Mu is the mobility, carrier mobility. So V is equal to mu Ex into H, and Ex is the applied electric field along the x-axis. This electric field is related to the current density and conductivity. This conductivity equation is well known, J is equal to sigma into E. Here we have considered the current density in x direction only, so the equation is written in the form of Jx is equal to sigma into Ex. So by considering the magnetic force, now we have come across towards the mobility more over the current density, and these two parameters are mainly important to identify the presence of charge carriers, or we can say mobility, inside the investigating material. And hence the hole coefficient, that is RH, is defined as Em upon Jx into H. So substituting the value of Em, that is equal to mu Ex upon Jx is equal to mu upon sigma is equal to 1 upon n into E. So this is the simple algorithmic calculation of hole coefficient. Em upon H is converted into mu into X, Jx is equal to sigma into Ex, so numerator Ex, denominator Ex is cancelled out. Finally we get mu upon sigma, that is the simple relation 1 upon n into E, where n is the charge carrier concentration and small e is the charge of electron. The most important, the dimension of hole coefficient is expressed in the unit centimeter cube upon coulomb. So this was all about the step A. Now we will move on to step B, where we are assuming that both types of charge carriers are presented, that means electrons and holes both are available inside the investigating crystal. It is important to recognize that for the same electric field Ex, the hole voltage for P carriers means positive carriers, that is holes, will have opposite sign from that for negative carriers, that are electrons. Thus, the whole field Ey will not be able to compensate from the magnetic force on both types of carriers, and there will be a transverse motion of carriers. That means the whole field, that is electric field, is now given in terms of Eh is equal to Ex into H mu H square. Mu H square is the carrier mobility of holes into P minus mu E square, that is the carrier mobility of electrons, into N divided by mu HP plus mu E N. For this case, finally, the whole coefficient is defined as RH is equal to EH upon Jx into H. Substituting the value of current density, that is equal to EH upon sigma EX into H. The final equation will be mu H square into P minus mu E square into N divided by E into mu HP plus mu En whole square. Since the mobility of holes and electrons, that are mu H and mu E, are not constants, but these both values are varying with the temperature. So these are the functions of temperature, capital T. The whole coefficient is also a function of temperature, and it may become zero even we have changed the sign of positive and negative charge carriers. In general, the carrier mobility of electrons are higher than the carrier mobility of holes, so that inversion may happen only if the number of holes are greater than number of electrons. Thus, hole coefficient inversion is characteristic of only p-type semiconductors, because in the p-type semiconductors we already know that the number of holes are much higher than the number of electrons. So thank you for visiting this lecture.